So, we will continue about the intensity of Bragg peak. So, in last class I used this picture, and here what I was telling that if we have scattering center, X-ray will fall and scattered in all directions, So, so this on this row, if other scatters are there, if their distance are say same, so then if for a particular direction I will get the scattered equivalent to reflected X-ray, and they will interfere, and this effect we will see. So, here they are just condition we have put here, this for constructive interference. Okay. If it is constructive interference, then these conditions are satisfied. So, it is equivalent to Bragg condition, not equivalent, similar to Bragg condition, but this another treatment Weiss process. So, this Lau treatment, and one can get from this concept one can get Lau equation. So, but I do not need this to know about the intensity of the Bragg peak, but what I need this concept, this scattering from an charged particle, from an electron, right. So, when X-ray scattered from these two centers, scattering center, if they are electron, okay. Now, it is so for one it can be for one this incident X-ray is falling with some wavelength and reflected one or diffracted one, it is diffracted with the same wavelength, but in different direction. So, this incident one it's say A, this wave equation I can write, in which way we write some amplitude and e to the power I omega t minus kx or kx minus omega t, whatever, kx minus omega t. Okay. So, that is the wave equation, equation we write like this. So, it represents the, say it is incident wave. Now, if I consider the another one, okay, if I consider, so in both cases incident one is this, right. Now, that is after reflection, whatever this in n2 direction we are taking, okay. Now, this, so these two will have some phase difference, okay. So, that because of this path difference, so equivalent phase difference will be, say for this scatterer at r distance. So, for this distance, so there will be path difference, this one, and this corresponding phase difference. So, one can write 2 pi by lambda to r dot n. Okay. So, that will be path difference. Okay. Now, so this your resultant wave is basically now after diffraction. So, it will be a e to the power I kx minus omega t, and now additional this phase difference will be there. So, I phi r, right. Okay. Now, this because of periodicity, this other will have this same similar will be it will have the same phase, right, phase difference between these to this, or it will have the integral multiple, right. So, what it is telling that X-ray is scattered by the electron. Now, if it is scattered by more than electron, so resultant effect scattering, after scattering, resultant intensity or amplitude, so that will be depend on their separation, position or their distribution, right. So, that is the point. If these electron from single electron whatever, if another electron is there, so then interference effect will be there, and that interference will depend on this path difference or phase difference, right. So, when X-ray scattered by atom, and atom is having more than one electron, right. Different atom has different number of electron and their distribution are different, they are distributed in different cell. So, if it is nucleus surrounding, right, so they are distributed in different way, okay. Now, X-ray is falling on it, it cannot be equivalent, it is scattered by a single electron, right. It cannot be single, right? It has, say here I have taken 8 electron I have taken. So, from 1 electron whatever the scattering strength, so it has 8 electrons. So, that total scattering strength, okay, or total amplitude, it cannot be 8 times of E, right. From single electron whatever the amplitude I am getting, when it will scatter from 8 electron, so it cannot be 8 times of this single one, okay, because of this there will be phase difference and there will be interference effect and the resultant amplitude or intensity will be different, okay. So, that is the point about this, because this X-ray intensity after diffraction from the crystal, okay. Those crystal we identify that crystal as a in terms of unit cell. So, now in unit cell, so as I mentioned earlier that it is enough to consider only one unit cell, because others are just replacement of repetition of that one, okay. So, that is why in unit cell the atoms or lattice points are distributed, right, and now in each lattice point or atom, so there are electrons are distributed. So, X-ray is scattered by electron, not by atom. So, now in atom, so when we will tell this scattered by atom, basically it is scattered by the all electrons. So, here that from one electron whatever the scattering strength, it cannot be multiple of number of electrons in that atom, it will be different from that. So that means that amplitude, square of that amplitude is basically intensity, right. So it will depend on the atom, right, how many electrons are there, how they are distributed there, right. So that is called atomic form factor, that is called atomic form factor, right. Atomic form factor. F, atomic form factor F. F is defined that amplitude of scattered X-ray or waves, amplitude of scattered X-ray by an atom divided by amplitude of scattered X-ray or waves by an electron. So that is called form factor. Okay. If it is just multiple of this one, so one atom is atomic number whatever, so that many numbers of electrons are there, Z. So this atomic number Z. Okay. So this is not simply just it is Z, right, Z times of this amplitude. Okay. So it is different. Why it is different, that we discussed, and that one has to consider. Okay. So it will be, so this F will be always, less than Z, except in forwarded direction. If they are scattered in forwarded direction, okay, then it can be Z. For any other angle, scattered in other angles, it is always less than Z. Okay. And this is, it is less than Z because of this interference effect, and that interference effect is coming because of the different position of electrons in a atom. Okay. So that's that factor has to be multiplied with the so this factor has to be multiplied with the amplitude of n electron, and from each electron it is just scattered, and thereafter there is no interference. So whatever the total, so that is basically Z times of this one, and with that this factor has to be multiplied. So then you will get the basically the what is called this actual amplitude of the scattered X-ray from an atom. Okay. So this is one factor is controlling the intensity of Bragg peaks, obviously, because so it is obvious that it depends on the basis, which type of basis, right, which type of basis, how many number of electrons are there. So, it will depend on the type of atom, right. So, this is clear. Second is the now these atoms, how they are distributed in unit cell. So, that is second important second part, and this is very important. So, that means it will depend on the structure of the crystal, right, because distribution of the atoms in crystal, it will follow the lattice point. Now, each basis is attached with the lattice point, right. So, which type of basis, that will be controlled by this atomic form factor, and then second it will depend on the type of the lattice, Bragg lattice, right. And yeah. So, as I earlier I discussed that for body centered orthorhombic and base centered orthorhombic. So, this distribution, number of lattice points are same, but distribution are different. So, the distributions are important. Why they are important? How it is contributing, controlling the intensity. So, that we would like to discuss. So, that is also it will depend on the structure of the material, structure of the lattice, right. So, that is why it is called structure factor. So, one can find the expression, basically this F equal to one can calculate, okay, but I will not do so. So, just here mainly I am giving you the concept, just qualitative concept. So, quantity that I will not derive, but it is not tough, it is really easy. So, if you wish, you can just try yourself, as we have given reference. So, from there you can try. So, but probably if you do not try also, this is fine, but this concept may be okay for this undergraduate course. So, the structure factor, so it depends on the structure. So, that is written generally F, and for a particular, it is for a particular plane, if I consider, okay. So, for different plane intensity will be different, that is obvious, right. For a same plane, what are the factors, how it is intensity is called. So, H scale plane, right. One should take a particular plane and then see what are the factors control the structure factor depends on what other factors, right. So, this H scale, so this now here also the same, that this scattering center. Now, we think this is the atom, right, X-ray are falling on atom, diffracted, right. So, your this path difference, so they will interfere, path difference, that whatever we got is not there. So, what we got, R dot n, right. So, that is the path difference, and that I wrote, so one can write this NH, say NH NH lambda, right, or just H dash lambda, whatever. So, here this is atom now. So, for each atom, what is the scattering strength, that I know from form factor, okay, for each I know, right. Now, again they will interfere, and depending on this path difference, we will get the resultant amplitude. Okay. So, this structure factor so is similar to this. So, definition also this similar amplitude of scattered wave by an unit cell. So, here by an unit cell, right, amplitude of scattered X-ray by an unit cell, divided by amplitude of scattered X-ray by an electron. So, whatever the one electron with compared to that, so from one unit cell as a whole unit cell, what are the scattered amplitude? So, this is by an electron, right. Okay. So, by an electron, now from that, because for other cases some interference effect will be there and amplitude will be modified, resultant amplitude modified. So, that one has to find out. Okay. So, it is obvious that this again because of this this your phase difference will be this now. If here we have written R, so now these similar things for atom, but amplitude is modified, basically this amplitude will be modified by factor f, right. So, here one can write, so you have many atoms, so if you take these two, now between these two what will happen? So, this amplitude, it is similar, this now this you can take, okay, this was for this one from one atom and then from other atom separated by R. So, what is happening? So, this same thing, okay. So, same thing you can use. So, it will be like this, resultant one will be like this, okay. So, your scattering amplitude one will get, so from each atom, if it is F, some say in unit cell n number of atoms are there at different position. So, one has to take summation, so Fj for each Fj, okay, from each from jth. So, j equal to 1 to n number, okay, whatever the number you have in unit cell. Now, it is from 1, but now it is modified, right, modified with this amplitude e to the power, it is modified with this amplitude with these phase factors. So, e to the power I phi r, right. So, e to the power I phi r. So, this I phi r, so 2 pi by lambda I 2 pi by lambda r dot n, okay. Now, if it is in unit cell, so this difference, so here as I mentioned that, so this n can be written in terms of reciprocal vector. So, one can write reciprocal vector, but here I cannot write just reciprocal vector keeping this factor. So, one has to use appropriate so it also depend on this h when you define. So, whether you are taking 2 pi there or not, okay. If you do not take 2 pi, so then you have to consider 2 pi here. If you take 2 pi there in B1, B2, B3 whatever we have defined, so then we do not need this 2 pi. So, these things are there. So, better you just keep it like n, okay. So, this now this R, it is for a particular lattice, this R will be So, this will depend on the it will depend on the distribution of this atoms in the crystal. Now, if same types of atom, so this factor Fj, this will be same for all. Okay. If different types of atoms are there, so for different atom F will be different. Okay. But for same type of atom, so here I am varying this J here. So, this the position with respect to, one has to take origin with respect to this, what was that distance r. Now, you have different position, right, you have different position, right. So, and for first atom, second atom, third atom, jth atom, so it's one has to write Rj. So, one has to write Rj, right. So, Rj will vary, right. So, for each atom, so if it is F1, so for that its position is R1, F2, R2, F3, R3, etc. If these atoms are same atoms, bases are same, then F1 will be equal to F2 will be equal to F3, okay. And F of course has come from here, one has to get this F. So, ultimately you will get this, so this structure factor, and the structure factor depends on the distribution of this. From this factor here you can see distribution of the atoms in lattice, in crystal, in unit cell, as well as this factor is telling that it depends on the type of atom, and there this value, this will be different. So, this one contains about the information, it depends on the type of atoms as well as it depends on the distribution of atoms in unit cell. Okay. So, this intensity, that is the intensity of X-ray, it is basically just, this is the amplitude, right, this is the amplitude of scattered one. So, one has to take F star, then it will give intensity, okay. And obviously, the intensity will depend on the type of atoms which is in this F and distribution of atoms which is here in phase part. Okay. So, now you know this. If so, one can just monitor, experimentally monitor if atoms is shifting from its position, original position, if it is shifted, so intensity changes, okay. So, thus from intensity one can study stress, right. Due to stress there is some, it is either contracted or expanded, okay. So, its intensity will vary, there will be shifting in this, if lattice parameter changes, shifting will be angle also. So, different type of information one can get from this intensity of Bragg peak. One information is type of atoms, type of bases. Second information is how the bases are distributed in the unit cell. So, from Bragg angle as well as intensity, angle as well as intensity, angle as well as intensity, both we need to know the complete detailed structure of the crystal, because not only lattice parameter, we would like to know what are the atoms are there and how the atoms are distributed, whether they are sitting at original position or whether they are shifted. So, all kinds of information one can get. So, as I told, this is a vast subject, and this just I try to give you this preliminary concept, but in details it is out of this course basically. So, one has to wait for the next for higher class, okay. But these are good enough if you understand whatever I try to tell you for your course. So, I will stop here. Thank you for your attention.